Okay, so in this video I'm going to kind of walk through how you do tensor vector multiplication operations. So we saw a lot of these in our transport class, and in my opinion, going through these operations, doing matrix operations rather than going through the Einstein notation or going through the summation notation, just using the matrix operations to get the answer is exponentially easier and it's far faster. So I'm going to explain how to do like a tensor dot product with a vector, a tensor double dot product, just the standard dot product, just all the dyads, outer products, all those kind of matrix operations or tensor operations that we were covering in transport. So first off, I'm just going to explain some basics of matrix multiplication. So if you look in this matrix in the top left corner, we have a matrix A, and it's of dimension m by n. So that's m rows by n columns. So this is element A11, so that's A row 1, column 1, and this is A row 1, column n, A row m, column 1, A row m, column n, and then it's going to be multiplying by this second matrix, which is of dimension n by w, so this is B n by w, and that's going to give you a product matrix, and I'm just calling each element C in this, so I have C11 all the way to C1w, so it's going to give you this product between A and B is going to give you a matrix of dimension m by w. So let me kind of explain when matrix operations or matrix multiplication is valid and when it's not valid. So if you have a matrix A and it's of dimension m by n, and you're multiplying it by a matrix B of dimension n by w, this is a valid matrix operation, and it's going to give you a matrix of size C, or it's going to give you a matrix C of size m by w. So the way that you can tell if a matrix operation is valid is you look at the inner dimension. So you look at this right here, and if these two dimensions are the same, so n and n, so these are the same, that means that it's a valid matrix operation. If they're not the same, then it's not a valid matrix operation. So assuming that it is valid, assuming that the inner dimensions match, then the dimension of the product, the resultant product of A and B, is going to be these outer dimensions. So it's going to give you an m by w matrix. C is m by w. So if we were looking at a converse case, say you had A with the dimension of n by m, and you're multiplying it by a matrix B with dimension n by w, these inner matrix or inner dimensions don't match, so this is not defined. It doesn't equal anything, so that's not defined. So with that basic concept, it's gonna, as long as you understand that, you can work through matrix multiplications, and it's going to be kind of the guiding principle showing you how to do all the tensor products. So the next thing I'm going to do is to show you how to approach multiplying a vector and a matrix, and then I'll actually go into the stuff that we were covering in class. Okay, so I just drew this matrix multiplied by a vector. So if you look at the dimension of matrix A here, there's 3 rows and 3 columns, so it's a 3 by 3 matrix. One second. So it's a 3 by 3 matrix, and if you look at this vector right here, there are 3 rows and 1 column, so it's a 3 by 1 matrix. Vectors only have 1 column dimension. So if you kind of use this rule up here of seeing if the inner dimensions match, you can see that we have a 3 by 3, so those match, so our resulting matrix multiplication is going to give us a 3 by 1 matrix, so we're going to get a vector from this. So the way that I like to think about how to approach doing a matrix multiplication is I like to take the matrix on the right hand side, you take the first column and you take it up, and then I imagine rotating it. So if I pick this up and I rotate it like this, so I have V1, V2, and V3. Then I multiply this element, V1, by this element here. And then I multiply V2 by this element here, and V3 by this element here. So my resulting matrix, and then you add each of those elements together. So I'll have V1, A11, plus V2, A12, plus V3, A13. So this is all just one term. This is one scalar, and it's going to be your top row. So now we do the same thing. I pick this matrix up and I apply it to the second row, and that will give me my second column of the resultant matrix. So I have V1, A21, plus V2, A22, plus V3, A23. And again, I pick this up and I apply it to this bottom row, and I get, I'll do that. I get a V1 multiplied by A31 plus V2, A32 plus V3, A33. So if you were to expand this concept, instead of looking at a vector right here, if this was a 3 by 3 matrix, at this point I would just take this second column and I would do the same exact thing. I would pick the second column up and I would multiply it all to this row, and that would give me my second column first row term. And then I pick this up again, my second column of my imaginary 3 by 3 matrix, and I would apply it to this second row here, and that would give me my row 2 column 2 term. And you just continue that. If you want more detail or more of an explanation, you can check out some of the Khan Academy videos. I'm sure there are plenty on how to do matrix multiplication. But that's all that I'm going to do. I'm going to now go to more of the stuff that is relevant to transport phenomena. Okay, so in transport, we are dealing with several different matrix operations. We're dealing with the dot product, the cross product, dyads, double dot products, etc. And the easiest way to get a handle on all of these operations is to know what order the resulting multiplication of these matrices is. So on page 808 of Transport Phenomena by Byron Bird, there's this table, and it gives you the order of the results. So when you're dealing with a vector, you have an order of 1. So a vector gives you an order of 1, and a tensor gives you an order of 2. And then if you're doing a dot product, you take you sum these up. You sum up the total number of multiplications by vectors and tensors, and you subtract 2 for a dot product, 1 for cross product, 4 for a double dot product. So with that in mind, we can kind of start working through how to do dot products, dyads, all those operations using matrix operations. And again, it's exponentially quicker and easier. So let's start with the dot product. Sorry for the bad handwriting there. So if I have some scalar a and I'm multiplying by this dot product right here, so u dotted with v, both of these are vectors. So if you look at the order, we have a vector multiplied by another vector, so that'll give you 1 plus 1, and then we're subtracting 2 for the dot product, so I'll write it over here. Order is equal to 1 plus 1 minus 2 is equal to 0, and a 0 implies a scalar, so it means that we're going to get scalar for an answer. So in mathematical notation, I'm going to transcribe this to mathematical notation. The way that you would write this is the dot product is defined as the vector u multiplied by v transpose. And the way to make sense of this is just to look at the dimensions. So U, we're going to assume is so let's go A multiplied by U dot V is equal to, so this is a 3 by 1, and this is a 3 by 1. So if you notice, the inner dimensions don't match. You have a 1 and a 3. So the reason why you transpose it is to swap these dimensions right here. That way the matrix is defined. So I made a mistake. This is actually not the dot product. This is the outer product, or how you do a dyad. So this isn't transposed here. Let me just back up. So the transpose is actually on the first vector. So it's U transpose V. So let me just go ahead and do an example. That way you can get the idea. So if we say U is equal to the vector U1, U2, U3, and V is equal to the vector V1, V2, V3, and we want to do the dot product of those two vectors multiplied by a scalar. The scalar is it doesn't really play a part in the multiplication. You just pull it out front. So A times U dot V is equal to A times the transpose of U. So we're going to flip it across the main diagonal. It's really easy, and if a vector, you just rotate it sideways. So you have U1, U2, U3. So that is a 1 row by 3 column matrix, and you're going to multiply it by V. So that'll give you V1, V2, and V3. So if I pick up this matrix, turn it on its side, then I'll have V1, U1 plus V2, U2 plus V3, U3. And all that is going to be multiplied by our scalar A. So if A times U1, V1 plus U2, V2 plus U3, V3. Okay, so if you look at the resulting dimension of this, so we have the inner dimensions match, and then the outer dimensions give us a 1 by 1 matrix, and a 1 by 1 matrix is a scalar. So these match, which is kind of the key point at why I'm bringing this whole order of result table into the mix, because that is really going to help us along with the more complicated matrix products. So I'm actually going to skip the cross product. I do the cross product with you just do the determinant. You go I, J, K, and U1, U2, U3, V1, V2, V3. And then you just take the determinant of this, and that will give you the cross product. I think that's probably the easiest way to do it. But that's not really matrix multiplication as I defined it earlier. So next I'm going to look at the dyad. Let me scroll down a little bit. So dyad, which in mathematical language is called the outer product. If you want to look it up in a math textbook for some reason. Whereas the dot product is called the inner product in mathematical notation. So a dyad is you have just two vectors right next to each other. So UV. So if we look at the order of that, I have 1 plus 1. And there's no matrix operation in between them, so you don't subtract anything from the result. So we're going to have an order 2, which is a tensor. So we're expecting a tensor from this result. So when you look at the outer product in mathematical notation, you would say that it's what I wrote earlier when I had to go back and erase. It would be U times V transpose. So the notation is kind of clunky, switching between typical mathematical notation and the way that the book does the notation. So I'm actually going to kind of disregard the typical mathematical notation because I think that's more confusing. But the way that you want to think about it is you just you take the normal first vector, so u1, u2, u3, and you multiply that by the transpose of the second vector. So v1, v2, v3. And if you look at the dimensions of this, we have a 3 by 1 by a 1 by 3. Inner dimensions match, so this is a valid matrix multiplication. And the outer dimensions are 3 by 3, which are, it's a tensor. Basically, a tensor is a 3 by 3 matrix. At least that's all we're going to be dealing with is 3 by 3 tensors. So if you go ahead and do this product, what you do is you take the first column and you multiply it by the first row of this matrix. So I'm going to have a u1, v1. And I take the first column and I multiply it by the second row. So then I have a u2, v1. First column, third row. So u3, v1. Second column, first row. It's u1, v2. Second column, second row. u2, v2, and then I'll have a u3, v2. Again, you go the third column, first row, so u1, v3, it's u1, u2, v3, and u3, v3. Okay, and then if you want to read out what your resultant matrix is, if you want to go to the E sub x or E sub y, E sub z Cartesian coordinates, everything in the top row is going to be your EX, everything in the second row is going to be your EY, and everything in your third row is going to be your EZ. So I'll write out the EX portion of it. So you can say EX multiplied by U1 V1 plus U2 V2 plus, that's actually a 1, U1 V2 plus U1 V3. And then if you want to get the next 6 terms, you can just multiply EY by the second row here and EZ by this third row. And that will give you all the 9 terms that you'd expect from this outer product or this dyad. So let me go ahead and scroll down and we'll look at a tensor vector dot product. Okay, so we're doing a tensor vector dot product. So you can either have the tensor first dotted with the vector, or you can have the vector first dotted with the tensor. And when you're in matrix land, things don't commute. So that means to say that tau dot v is not the same thing as v dot tau. So order matters is another way of saying that things don't commute. So let's take this first case. It's a little bit simpler. So we're doing the dot product. Let's go ahead and first off actually look at the order. So we have a tensor, so that gives us 2, and we have a vector, and that gives us 1. And then we're subtracting 2 for the dot product. So the resultant order of the multiplication is going to be 1, which implies that our answer is going to be a vector. So if we look at tau, tau is a 3 by 3 matrix, and V is a sorry, it's not equal to, is a 3 by 1 matrix. So if we look just at, if we were to multiply them as I wrote them right now, if we were to just do the multiplication like this, you would see that the inner dimensions match, and then the outer dimensions would give us a 3 by 1 matrix, which is a vector. So this is actually all you have to do to get the vector tensor dot product when tau is the first term and the vector is the second term. So I'll go ahead and walk through that multiplication. So you have tau 1 2, sorry, not 1 2, 1 1, tau 2 1, tau row 3 column 1, tau row 1 column 2, tau 2 2, tau 3 2, and just finish writing it out here. And then we're going to multiply it by the 3 by 1. So V1, V2, and V3. And then if you can imagine picking up this vector, rotating it sideways, and then multiplying this element by this, adding this element multiplied by this element multiplied by this, and that would give you the first row of the resultant vector. And then for the second row of the vector, you're going to get V1 multiplied by tau 2 1, V2 multiplied by tau 2 2, V3 multiplied by tau 2 3. Okay, so I just did a little bit of that quickly, spared you some time. I'll do the last one with showing you how to do it. So tau 3 1 V1, so I'm taking this, multiplying it by this, and then I'm adding V2 multiplied by tau 3 2. So tau 3 2 V2 plus tau 3 3 V3. So this is just a scalar because these are additions in between here. So this is only a 3 by 1 matrix. So again, we were expecting a vector by looking at the order, and that's what we got. So this is these are the three terms in our vector. And again, if you wanted to read them off, you can multiply each term, or this one term in the top row by e sub x, the second row by e sub y, the third row by e sub z, or whatever coordinate system that you're working in. So I'm going to scroll down, and then we can look at the dot product for the other. So if we were looking at v dot tau, so if we were again to look at the dimensions, you can see that 3 by 1, and then we have 3 by 3. So the inner dimensions don't match, so this is not a valid matrix operation as written. The dot product is definitely defined. That is a real thing, but we just can't multiply left to right like this. What you actually have to do is you want to switch the order of these two and transpose tau. So it would be tau transpose, and then you're going to multiply that. So that's a 3 by 3, and you're going to multiply that by your vector. Inner dimensions match, outer dimensions give us a vector. So that's the right order. I don't actually have a precise mathematical reason why this is true, but you can test it out for yourself, validate it yourself. If you want to go through and check that the answer that I get is the same as that you would get from Einstein notation or summation notation, this just works. So let me go ahead and quickly tell you how to transpose a matrix. So what you do is you take everything that's in a column and you put it to the rows. So I'm going to transpose T here. So I'll go tau 1 1, and then I'm taking this term and putting it here. Tau 2 1, tau 3 1. So now I'm going to take the second column and I'm going to put it in the second row here. Tau 1 2, tau 2 2, tau 3, 2, and finally I'm going to take the third column and put it in this third row. Tau 1, 3, tau 2, 3, and tau 3, 3. Okay, and then I'm going to multiply that by V1, V2, and V3. So I'll save you the trouble of watching me actually do all that. 1 second here. Okay, so if you go ahead and do the multiplication, you take this column, multiply it element-wise, you get V1, tau 1, V2, tau 2, 1. That will give you your top row, and just do the same process as we've been doing, and you'll end up with this resultant, which is a 3 by 1. And again, this is 3 by 3, 3 by 1. Inner dimensions match, outer dimensions give us the vector that we were looking for by looking at the order of tensor multiplied by a vector. So the last operation that I'm going to look through is the tensor double dot product. And just give me 1 second to get some blank real estate and I'll be right back. Okay, so we're looking at the tensor double dot product now. So we're going to have tau double dotted with sigma. Both of these are tensors. So if we look at the order, and we're going to get 2 plus 2 minus 4 equals 0. So you get minus 4 for a double dot product. 0 is going to imply that we're expecting a scalar from this operation. So the double dot product is a little bit different because it's not a traditional matrix operation. It's actually element-wise multiplication. So all you're going to do is take sigma 1, 1, multiply it by tau 1, 1, and then add that to sigma 1, 2, multiplied by tau 1, 2. So the result of this operation is just going to be a 1 by 1 matrix. So pay special attention to this double dot in the middle. This is not traditional matrix multiplication. So I'm going to write this out now. So it'll take a few minutes. So tau 1, 1, sigma 1, 1 plus tau 1, 2, sigma 1, 2 plus tau 1, 3, sigma 1, 3 plus tau 2, 1, sigma 2, 1 plus tau 2, 2, sigma 2, 2 plus tau 2, 3, sigma 2, 3 plus tau 3, 1, sigma 3, 1 plus tau 3, 2, sigma 3, 2 plus tau 3, 3, sigma 3, 3. So the double dot product is pretty easy. It's a little time consuming to write out all those additions, but this is just a scalar. This is not in a matrix. This is just this term plus this term plus this term plus this term. But I find that if you write it in this like quasi matrix form, it makes it easier to kind of see the relationship of how you're going from this double dot product to this. So this is just a 1 by 1 matrix, if you like. Scalar. I can't spell, but it's a scalar, and that's kind of how you go through all the vector and tensor notations using matrix operations. And again, it is exponentially faster, so hopefully you'll find this useful.